if V is finite dimension over F, then any two bases of V have the same number of elements. So we have to prove that if V is a finite dimensional vector space over the field F, then any two bases, you take any two bases, they will have the same number of elements. Okay, so I take two bases. I take v1, v2, vn is one basis of V, and the other basis I take as this w1, w2 till wn is another basis of the same vector space V over the field F. Now, so if you use this lemma, so remember we have done already in the previous video about this lemma. If v1, v2, vn is a basis of V over the field F, and if w1 are linearly independent over the field F, then m should be less than equal to n. So we have this property. Now since this is the basis of V, and this is also a basis, so any basis is always linearly independent. So this set is also linearly independent. So this is a basis of V over F, and this will be linearly independent. Since this is basis and this is linearly independent, we can use the above lemma. So we get here m is less than equal to n. So we get here m is less than equal to n, that we took as equation 1. Okay, similarly this is the basis of V over F. Okay, and this is the basis. Since it is a basis, it is linearly independent, so this set is also linearly independent. So this is a basis and this is linearly independent, so we can apply the lemma. So we get here n is less than equal to m. So from 1 and 2 we can see that a number cannot be less than equal to n as well as smaller than m. So these two numbers should be equal. So we have that m equal to n, hence the result. So we'll try to do this. Remarks, we have written some remarks here. So remark 1 is, if Fn is isomorphic to Fm, if and only if these two fields, okay, will be isomorphic to each other if and only if this n is equal to m. So if and only if n is equal to m. And the remark 2 says that if V is a finite dimensional vector space over the field F, okay, over the field F, then V is isomorphic to Fn for a unique integer n. So this V will be isomorphic to Fn for only a unique integer. It is not that for any integer n it will be isomorphic. So only on a specific n it will be isomorphic. In fact, that n is the number of elements in any basis of V over F. So n is nothing but the number of elements in that basis set of V over F. Now remark 3 says that any two finite dimensional vector space over the field F of the same dimension are always isomorphic. So if you have any two vector space, they have the same dimension, then it will be always isomorphic. Okay, so lemma, we are going to prove this lemma. So if V is a finite dimension over F, and if u1, u2 till um belongs to are linearly independent, then we can find vectors, these vectors in V, such that this will become a basis of V. Okay, so we can find a basis. Now here in this theorem, say in this theorem we are taking here, since V is a finite dimensional vector space, so it will have a basis which is finite. Okay, so I'm taking a basis here. So v1 till v2 till vn, v1, v2 till vn is a basis of V. So I'm taking this to be the basis of V. Since it is a basis of V, this is capable of spanning the whole vector space. So this will span V. Spanning means nothing but if I take any vector in V, this can be written as a linear combination of these vectors. Okay, so that is the meaning of spans. Now this vector, so this u1, u2 till um are linearly independent. Okay, so this one is also linearly independent. Now we can find a subset this of, means we choose like this. So we have two sets. So this is your consisting of u1. This is consisting of u1, u2, u3, so on. Okay, and this is consisting of v1, v2, v3, so on till vn. This is linearly independent, this is linearly independent, so we can take together this big set u1, u2, u3, so on, v1, v2, so on till vn. Okay, we can choose this So we can take one set. Okay, from here this set is already linearly independent. We know this one. Okay, this one is linearly independent. So from we are taking this set is already linearly independent. I can choose some vectors from here. Okay, I'll choose some vectors. Not all these vectors will be linearly independent with this. So I'll choose some vectors from here which is linearly independent for this. For example, I take vi1. So this I'm choosing this vi1 from here. Okay, which will become linearly independent with this all these elements. And I'll choose same way I could choose another element vi2 which will be linearly independent with this, and so on till vir. So this will be linearly independent. So if I put this together with u1 u2 till um, then this whole set will be linearly independent. Okay, this consists of linearly independent, and this set will be capable of spanning V, the vector space over the field F. So this set is capable of spanning the vector space over F. So this become a basis. So in particular, okay, we'll try to choose this vi1. We'll try to take this vi1 as u m1 plus 1. This will choose as um plus 2, and so on till here we'll choose as plus r. So this will become a basis for the vector space. So if that is a linearly independent set, we can construct a basis which can span the whole vector space. Hence the theorem. Thank you.